here I'd like to give you an example of using the second derivative test to find extreme values of a function. Now remember, this has limited applications and limited results, so we can always use the first and second derivative test to find the extreme values and the points of inflection. However, sometimes it's more efficient to use the second derivative test, and this is one of those cases. So first we want to find what this function is as just a polynomial. So we'll multiply it out, 6 minus 2x times 6 minus 2x. Hold the x and FOIL the last two. 6 times 6 is 36, minus 12x, minus another 12x, plus 4x squared. Then multiply all the things by x. So we get a new original function that's a little bit easier to differentiate. 36x minus 24x squared plus 4x cubed. From there we can find the critical points. Remember, those critical points come from the first derivative or endpoints. There are no endpoints of this function, so let's find where the first derivative equals 0. That's 36 minus 48x plus 12x squared, where we could factor out a 12, so that's 12 times, and let's turn the function around, x squared minus 4x plus 3. We care where that first derivative equals 0. That's at 12x minus 3 times x minus 1 equals 0. So the solution, so the first derivative equals 0 at 3 and 1. Those are critical points of the first derivative. Maybe you call them critical points of the first derivative, critical point prime. Now that we know where those critical points are, remember we have this. Should not make it a closed endpoint because we have no limited domain here. It's just unlisted, so we can assume negative infinity to infinity for this polynomial. And we have two places, 3 and 1. Oh, look what I did. That's not where they live. 1 and 3 in order, right, where they belong on the number line. That could be max or minimum values of the function. Now we could use the second derivative test, which means that number 2, split up the value. Number 3, test f double prime or y double prime at the critical points. So in this case, we have two critical points, 1 and 3. We want to know what their concavity is. So let's find the second derivative. This y double prime, looking up at y, derivative of 36 is 0. We get negative 48x plus 24x. Excuse me, not negative 48x, but negative 48 only plus 24x. It's a true second derivative. So we test this second derivative at the critical points. We want to know what y double prime is at 1. That's negative 48 plus 24, which is negative 24. That means that at 1, the function is concave down. So not only is it concave down, but it's concave down and we have a critical point of the first derivative, so 1 must be a maximum value of the function. And then we can test the second derivative at 3. That's negative 48 plus 24 times 3. It's a big positive value, because 3 times 24 will be bigger than 48. That means that this function is concave up at 3. So not only is it concave up, but it's also a critical point of the first derivative. Then those two criteria are met, we have a minimum value of the function. Now from this, since we know we have a max and a min, we can talk about the behavior. The function must be decreasing and then increasing and then, oh, that doesn't make sense either, right? If it's a maximum, it must be increasing and then decreasing and then increasing again. That's the only way to get a max and then a min. So we know the behavior of the function and now we know values. So we could say that there is a maximum at x equals 1 and a minimum at x equals 3. We also know that these are both relative because the ends of the function, at negative infinity it goes down at negative infinity, at positive infinity it goes up to positive infinity, so these are both relative extreme points by the second derivative test right here that we used.